This. All right, everybody, we'd like to get started. So the first talk of this session is titled Arithmetic Sketching. And this is work by Dan Bonet, Alette Boyle, Henry Corrigan Gibbs, Niv Gilboa, and Yuval Ishai. And Henry will give a talk.
Great. Yeah, thanks so much. And thanks all for coming. I'm wondering if you thought this was like a machine learning session or cryptocurrency. This would be much more interesting, I promise you. So a super common task in cryptographic protocols is we have a big vector.
Henry, hold on. Sorry to
stop
you. We don't have slides up there yet.
Excellent. So big vector that's secret shared amongst a number of parties. Can I? This way? This way. My formula lab. My former labmate said I'm close enough to throw tomatoes at. So, all right. So you have a big vector that's secret shared amongst a number of servers, and the servers want to test some property on the vector. So, for example, does this vector have Hamming weight 1? They want to do this without revealing anything else about the vector. More generally, you can think about the servers wanting to test whether this vector X is in some language, say language of vectors of Hamming weight 1 or something else. So the complexity measures that we care about when we're doing this typically are the computation times for the servers, the communication costs in terms of the number of bits exchanged, and the interactivity or the round complexity of the protocol. So this actually comes up in a ton of cryptographic protocols, and often the language that the verifiers want to kind of check membership in is pretty simple. So for PIR writing and private messaging, they're trying to test like Hamming weight 1. For private advertising and private analytics, maybe Hamming weight 1 with the non-zero elements in a specified set. Bounded Hamming weight is also common, and something I'll call the L1 norm, which is essentially the sum of the elements of the vector, where they all have to be, say, between 0 and W. So you may have seen these in some protocols yourself. So the way we tend to solve these problems in crypto today is kind of a special purpose protocol each time the problem comes up. So there's a bunch of really, really clever protocols in the literature for doing this. And in fact, some that influence our work. The limitation, though, is it's not really clear when you have a protocol, say, for Hamming weight 1, how does this extend to checking Hamming weight 2? Or if you're testing membership in one set, can you extend the set? Like, how does that work? In addition, many schemes require a prover to provide some kind of auxiliary proof information to the verifiers to help them check this statement. And in some cases, there just isn't a prover, and a multi-party computation often there isn't. And the last thing is it's not clear whether these protocols are optimal in terms of the various complexity measures I mentioned. So the goal of this paper is to kind of do three things. The first thing we do is we give a new abstraction called arithmetic sketching that tries to capture all of these kind of the core of all of these prior schemes that are in the literature. And you can think of it as kind of the information theoretic components of these cryptographic protocols. What we show is that if you have a sketching scheme for a language L, then you can compile that sketching scheme into a multi-party protocol for testing whether a secret shared vector is in some language. And I won't be talking about it, but these similar ideas apply when you have a committed or an encrypted vector with a linearly homomorphic scheme. So that's the first thing, is the new abstraction. The second thing is we give new sketching schemes for simple languages like the ones I just mentioned. And this immediately gives us new protocols for testing properties of secret shared vectors or committed or encrypted vectors. And then the last thing we do is we prove some lower bounds, showing that in certain cases, in certain cost metrics, the new schemes that we give are optimal. So, okay, let me tell you first about what arithmetic sketching is. It's actually, I'm going to try to convince you it's a very simple and natural idea. So an arithmetic sketching scheme is defined with respect to a finite field F and a language L. And what it consists of is two algorithms. There's a sketching algorithm and a decision algorithm. So what the sketching algorithm does is it outputs a linear map. You can think of this as a matrix that takes the big input, X, and shrinks it down to a small sketch of the input. So you think of this as being much, much, much smaller than the input. And then the second algorithm, this decision algorithm, takes the sketch as input and outputs a single field element, which should be 0 if X is in the language and non-zero otherwise. So you can think of the sketch as kind of like a compressed representation of the input that sort of keeps information about whether the input's in the language or not. And the key property of this decision algorithm is that it's an arithmetic circuit. So yeah, sometimes I'll think about the sketching algorithm as making linear queries or inner product queries to the input, but this is just kind of same thing going on. So a little bit more formally, here are the two algorithms, or the syntax of the two algorithms. I'll call L, which is kind of the sketch size, use L to denote the sketch size. And then the decision algorithm, I'll think of it as outputting a single field element, but it can be a vector field element. So the reason why we call this an arithmetic sketching scheme is this restriction that the decision algorithm is an arithmetic circuit whose size and structure is independent of the field and the input size. That's actually what makes the sort of abstraction non-trivial or difficult to achieve. So in particular, if you don't have an arithmetic decision predicate, then taking a random linear combination is enough to kind of sketch any sparse language. But a random linear combination, like deciding whether a random linear combination of the input is in a language or not, that's actually not easy to do with an MPC. So kind of requiring that this thing be an arithmetic circuit is what makes it useful for cryptographic application. For those of you who've seen linear PCPs and fully linear PCPs, you can think of this as like a fully linear PCP without a proof. But if you don't know, don't worry about it. So the two properties that we ask of a sketching algorithm are completeness and soundness, which just says if X is in the language, then the sketch should accept always. And if X is not in the language, then the sketch should reject with high probability over the randomness of the sketching algorithm. So good. Now that we have the abstraction, let me show you how to use this to test properties of a secret shared vector. So think of two servers as having shared with this big vector X. What they can do is use correlated randomness to run the sketching algorithm. That outputs this linear map. And so locally, they can compute this small sketch of the input. And then given the sketch, or shares of the sketch, they can run in a multi-party computation this decision predicate on the sketch. And they accept if the sketch accepts and rejects otherwise. So completeness and soundness here follow immediately from essentially the definition of arithmetic sketching. In addition, we want some kind of privacy property, right? That the output of this multi-party protocol doesn't leak more than the fact that X is in the language. And in fact, sketching schemes, when compiled in this way, give zero-knowledge protocols in the following sense. So if X is in the language, the output of the sketching scheme is always 0. So it leaks nothing about X apart from the fact that it's in the language. We can even get a stronger kind of notion of privacy, a two-sided, what we call two-sided zero-knowledge, which is that whether X is in the language or not, the only thing that leaks is the single bit of whether X is in the language. And that you can do once you have an arithmetic sketch just by randomizing the output of the sketching scheme. So this like privacy, completeness, and soundness all follow pretty naturally once you have an arithmetic sketch. So the complexity metrics that we care about are 3 here. So we care about the sketch size, which dictates the time to compute the sketch from the input. We care about the multiplicative complexity or the size of the decision predicate in terms of the number of multiplication gates, and that dictates the computational communication costs in an MPC. And then the last thing we care about is the degree of the circuit, which dictates the round complexity. Okay, that's the entire abstraction of arithmetic sketching. In the remainder of the time, I want to discuss how we construct sketches for these simple languages, and then I'll finish with a little about. So in the paper, we give a few different constructions. So first, we give a new way to construct sketching schemes for vectors of weight 1, Hamming weight 1. We also give schemes for bounded weight vectors, so like weight 5 or weight 10, and also this bounded L1 norm. So essentially, the sum of the elements is bounded by something, and each element individually is bounded as well. So for these second 2 languages, we give the first constructions, actually. And for the first construction, the weight 1 vectors, we're kind of unify some existing ones and then also give some constructions there as well. And the other thing we do that I won't talk about is show how to get malicious security for this kind of MPC compiler. So let me start with the weight 1 case. So we kind of give you a recipe for constructing sketching schemes for languages vectors with weight 1, where the payload or the non-zero value lies in a certain set. And the way we do it is,
Oh, say.
no worries.
We're gonna check really fast if this is muted.
No, it's not.
It's not muted? Okay. Thank you.
All good?
Yes.
Cool. So, okay, so we show that if you have some kind of polynomials with certain structure that I'm not going to tell you about, you can get what's called an S sketching distribution. And that that construction, that stuff is in the paper. But from an S-sketching distribution, you can get an arithmetic sketching scheme for weight one vectors, where the payload or the non-zero element is in the set S. And the second part I am going to try to describe for you. So the first thing I have to tell you about is this S-sketching distribution, which is a new object we define in this paper. And it's inspired very heavily by AMD code, though it's not exactly giving you an AMD code. So an S-sketching distribution consists of two algorithms. It's a sample algorithm, which outputs a vector, and a verification algorithm, which takes as input a vector and outputs kind of one field element, telling you whether to accept and reject. And these algorithms are defined with respect to some set S. So these S-sketching algorithms should have three properties. So the first is completeness. So if you take a sample from this distribution and you scale it by some value beta in the set S, the verification will accept. So the verify accepts all samples that are scaled by some permitted values beta. Soundness says that if you scale by some non-permitted value beta, so some beta that's outside the set S, then verification should reject with high probability. And then also, you shouldn't be able to shift any sample by kind of an additive offset. So if you take a sample and you add some garbage to it, the verification algorithm should also reject with high probability. So now I just wanted to show you a very simple construction of an S-sketching distribution for the set -1, 0, and 1. So the sample algorithm just takes a random R and outputs R and R cubed. And the verification algorithm just checks that the first element cubed minus the second is equal to 0. And why this is an S-sketching distribution, so you can see that if you have a sample and you scale it by -1, 0, or 1, the verification algorithm will still accept. And if you scale it by something else, you can see with a little bit more thought that verification will reject. So this gives you a very simple construction, but it's already doing something kind of nice to do. So now we need to show that if you have an S-sketching distribution for some set S, you can construct an arithmetic sketching scheme for the language of weight one vectors with the payload. And this construction is also pretty direct. So what you do is the sketching algorithm runs this sampling algorithm n times. So n is the length of the input to the sketching scheme. And it uses these n samples as a sketching matrix. So it takes the n samples and kind of arranges them into the columns of the sketching matrix. I'll show this in a second. And then the decision algorithm just applies the verification algorithm for the S-sketching distribution. So let me show you the same thing in picture 4. So we run kind of the sampling algorithm once for each column of the sketching matrix to construct this big L by N matrix. And we apply that to the input to get this sketch. And the sketch is the size of the sample from this S-sketching distribution. And then we just run the verification circuit for the S-sketching distribution to test whether or not we're going to accept or reject. And to try to sort of argue why this makes sense, so in terms of completeness, if the input vector actually is all zeros with permitted value beta as the payload, what the sketch is going to consist of is a sample from this S-sketching distribution scaled by beta, and the verification algorithm will accept. But if there are more than one non-zero entries in the input, or one of these is kind of, it's weight one, but not with a permitted payload, then you're going to get some garbage down here. So not a sample scaled by beta, but scaled by beta with some offset, and the verification algorithm will reject. So we use this framework to construct sketching schemes for some new languages and also kind of unify existing constructions. So there's some really clever constructions from the CGI 16 paper for these two sets, which kind of fall into this framework. And then we give some new ones. In fact, the first constructions where the payload is unconstrained, and also for these kind of uploading, downloading applications using this idea. So that's kind of the second part of constructing arithmetic sketching schemes for weight one vectors. And again, the first part, I'll refer you to the paper. So the last couple things, constructions I want to show are for bounded weight vectors. And here I'm going to be pretty sketchy. Yeah, I was tempted to make many sketch puns, but that's the only one I'm going to make for these constructions, just because they're a little bit more involved. So the basic idea for skipping weight W vectors is that we view the input to the sketch is the coefficient vector of a polynomial of degree at most n. And then with a linear query, or kind of one row of the sketching matrix, you can evaluate this polynomial at any point of your choosing, just by using the vector of 1, r squared, r cubed, 4, and so on. It turns out then that there are existing polynomial sparsity tests that allow you, using only black box access to a polynomial, to check whether this polynomial has few coefficients, so fewer than w coefficients, or more than w coefficients. And so we can kind of put these two things together. We basically run this polynomial sparsity test, and it's going to ask us to make some evaluation queries to the polynomial. The sketching algorithm can make those evaluation queries, and then we just run the decision routine for this polynomial sparsity test, which requires computing a determinant of a little matrix. So that's the idea for that construction. The most involved construction maybe is the sketching for the L1 norm. Again, the entries and all entries in the vector are between 0 and w, and they sum to w. So here, what we do is you make a bunch of linear queries, so roughly w linear queries of the form random 1 to the I, random 2 to the I, random 3 to the I, so kind of powers of random elements. That's what the sketching matrix looks like. And what the answers to these kind of linear queries or the sketch outputs look like, if you make queries of this form, are power sums. So there's some z1 up to zm that look like this. So the sums of the zi's, the sums of the zi squared, and the sums of the zi's for the w plus 1 power. And this number m here, kind of the number of terms in the sum, it ends up being the L1 norm of the input vector. And then you can use the Newton relations to kind of massage things that look like this into some values that let you test whether the L1 norm is bounded. So that was a very high level thing that I don't expect you to understand. Very sketchy, but yeah, that's the basic idea. Check out the paper here. So those are the new constructions. Kind of the last piece of the paper is showing that these protocols, these new sketching schemes, are optimal in terms of certain parameters. So we give two types of lower bounds in the paper. So the first is from algebraic techniques. We can prove things like there isn't a sketching scheme for weight 1 vectors. That's with kind of unconstrained payloads, where the sketch size is at most 2. So what that means is that we have a sketching scheme in our paper that has sketch size 3 for this language, and that's optimal in terms of the sketch size. The second kind of lower bound is from communication complexity, where we can rule out any arithmetic sketching scheme for certain languages. So for example, the language of schemes with like vectors, the language of vectors that have at least one value in a certain set S, there is no arithmetic sketch for that language. Or all zeros with a run of ones somewhere. There's also no sketch for that language. So yeah, it's kind of nice. Once you have this abstraction, information theoretic abstraction, it's easier to reason about what's possible and what's not possible. Okay, so arithmetic sketching, just to wrap up, the kind of one idea you should take away is you have a big input, you apply a linear map to it to squish it down, and then you apply a small arithmetic circuit to test whether the input has some property or not. And I'm hoping that this is like a simple, useful tool in some cryptographic problem you have in mind. And I think there's still a bunch of questions you could ask about these schemes. So can we improve the complexity of the sketching schemes that we have in the paper? Can we expand the set of sketchable languages, so sketch new things that we didn't know how to do before? And are there kind of useful approximate notions of sketching? We didn't even touch that problem in this paper. So paper's online, and I'm happy to take questions at this point.
Thank you very much. Any questions? Online folks, if you have any questions, feel free to put them in the chat.
I'm in the back.
I say in the back. Okay, can you come down and to this microphone here? Well, the problem is online people won't hear you if you yell.
Thanks for the talk. For your W sketches, hello? Oh, I'm just not close enough. For your W sketches, is it arbitrary W, or do you assume like an upper bound on it, like?
So there's no upper bound on W, but the complexity of the sketch, so the sketch size and the size of the decision circuit will depend on W.
Right, that's the point. So do you have another scheme for like full weight W? Because you mentioned like some people care about W being full weight, right? Like it's like length N. Do you have like a more efficient scheme for that setting, or is it something you have to talk about?
Yeah. So once W grows to be the size of N, then these sketching schemes are not probably the right tool for you. When basically when the language is dense, which is sort of what happens in that regime, it's not useful for it's, I would say, more useful in the sparse case. Yeah, great question.
Any other questions? So I have a question. So you restricted your decision procedure then to being linear, right? Is there a reason, like what would happen if you allowed, say, degree 2 or something slightly more complicated that enrich your class that you're able to support, or?
Yeah. So we have this linear map that's taking the big input down to a small thing, and then an arithmetic circuit, which could be degree 2 at the end.
I see.
I think the one question is like, if you took a linear, instead of a linear map, you took a degree 2 function, what could you do?
Right.
Yeah, we haven't looked at that. And that would make sense in settings where you have multi-party computations where degree 2
Right, it's still cheap, it's still communication.
Yeah,
still okay.
exactly. No, it's a great question.
Yeah.
As far as I know, we haven't thought much about it.
Okay, so any more questions? All right, if not, let's thank the speaker again.
Thanks.
We need to share or resume share. Right.
Yeah, and if you go to more, it's recording, so yeah, I think we can only find
It's
it.
still recording, yeah. I don't see where the slides are. No, they're not
I
here.
think they need to switch it. Yeah, you can switch it. Just the recording was paused, so.
Oh, okay, yeah, sure.
Yeah.
Did you switch the, like, do you have the slides up?
But I don't see
Yeah,
the
yeah.
slides are up, but they disappeared for some reason.
Oh,
Yeah, they're fine.
oh, okay. Weird. Oh, yeah,
Here are
so,
the slides.
okay, did you change the sharing to be this one?
Just like let's do new share.
You share, yeah.
Thank you.
Screen.
Screen. Or no, we should rather do this.
Yeah, we
right?
can do that one. Great.
Yeah,
Yeah, as long as it's like.
yeah, I'm not seeing, here it is. Okay, there we go.
Is it? No.
No, you just slide up there.
There's the link.
Yeah, cool.
Yep.
Those are good.
Hey, I'm shy, 1 second. There we go. All right, so our next talk is titled Additive Randomized Encodings and Their Applications. And this is work by Shai Halevi, Yuvali Shai, Eyal Kushilevich, and Tal Rabin. And Shai will give the talk.
Thank you, Arkady. All right, let's jump right in. Well, can we?
Hold on.
Really?
Right now?
Yeah, thank you. So the starting point is computing the sum. When you have a multi-party computation setting and parties, each one of them has their input, all you want to do is the sum of them.
Actually, only share
This is secure computation 101. This is the easiest task that you can possibly have
in this-
in many different settings, in many different
Yeah, I'm
ways.
shy. 1 second, we're having.
Yeah.
Sorry.
I mean, yeah, it's only sharing the title screen right now.
So why is that the case?
Oh, your screen, oh, yeah, so I guess like fix the,
You share this, right? This is what you should be sharing.
let's just do screen then.
I
Okay,
think we need to do screen.
do what?
The screen.
Oh, screen, okay.
Yeah, let's just do screen and then share that and then make sure to hide the little bottom thing. More and then hide. Yes.
Okay, please go ahead.
Good, thank you. So, as I said, we're starting by just thinking of computing the sum, which is the easiest secure multi-party computation that you can have. And perhaps you can think of this walk is this thought of what if this was enough? What if all you needed to do with MPC just required that? More specifically, could it be the case that any function, multi-party function that you want to compute f, could be computed by first having the parties locally encode their input in some way, then computing the sum, and then decoding the sum into the value of the function that you want? Wouldn't that be nice? And it seems awfully optimistic, but maybe not that crazy. I mean, we do have interesting things that we can do using the sum. So just two examples, the private system, does private aggregation, basically using computing the sum. Or if you think of federated machines learning. We know how to do a lot of things in federated machine learning, basically by computing the sum of things. So somehow we ask, what can we compute if all we have is an oracle for computing the sum, and over whatever a billion group that you want. Formally, we have this notion of additively randomized encoding that consists of maybe a setup procedure and then an encode and decode procedure, where parties locally encode their input, then you sum it up by the oracle, then you decode the output, and a simulator for security. So what we require is the notion of correctness, of course. If everybody does what they're supposed to be doing, then the thing that you get after decoding is the value of the function. And secrecy. You have a simulator that given only the output of the function can simulate the view of that protocol. And as usual, simulating the view, you can think about it as either perfect simulation, statistically close, or at least computationally distinct. So just to demonstrate how that thing works, let's think of the OR function. N parties, each one with single bit of input. What you want is to compute the OR function. 0 if all of them are zeros, 1 otherwise. So here's a additively randomized encoding scheme for the OR function. You walk over some large enough ZQ. Every party looks at their input. If their input is a 0, then they encode it as a 0 in ZQ. And if their input is a 1, then they encode it as a random element of ZQ. And then you sum it up. And the decoding looks at the sum. If the sum is 0, then it outputs 0. If the sum is anything else, then it outputs. So it's very easy to see that this has one-way correctness error of 1/q. If everybody gets 0 as their input, then the output of the function will be 0. But if it's not, then there's still 1/q probability that the output will be 0. From security point of view, however, it gives you perfect secrecy. Right? The simulator just output. If the bit that the simulator sees is 0, then it outputs 0. Otherwise, it outputs a random value, and this is the exact right distribution. Just to put it in perspective, for those of you who know about the general concept of randomized encoding, the thing that's new here is you separate the local encoding from the global addition. And this lets you get by with the global addition being a degree 1 function, that is just the sum, whereas for randomized encoding, you need higher degree than 1 in order to be able to get randomized encoding. All right, so what do we have? What can we say about it? Well, the main result, and one that I'll talk about in this presentation, is saying that this crazy notion that you can compute every function, that actually is true, at least in the computational setting. Assuming some DDH-like harnessing by linear map groups, every function has a computational additively randomized encoding scheme. And I'm going to talk about some corollary for that for the shuffle model, and in particular, how you can use it to get a general purpose compiler that takes any centralized differential private scheme and turn it into a differential private scheme in the shuffle model. Other things that are in the paper, but I will not have time to talk about today. There's some upper and lower bounds on statistical and perfect AREs, and there's the notion of robust ARE, which is what happens if you think of a collusion between the evaluator that sees the sum and some of the input parties. So if you want to get security even in that context, then that's a much stronger notion of security. In particular, it implies obfuscation. We show how to construct it in the ideal obfuscation model, and we connect to other notions like best possible information theoretic MPC and multi-party randomizing. So the next thing that I want to show you is that every function has a computational area, assuming something about DDH-like assumption. And the main step in this is showing that this function has an additively randomized encoding, the equality function. 2 parties, 2 inputs, What you want is to compute whether or not they're equal. The value of the function is 1 if they are equal and 0 otherwise. Once you have that, you can use it to get oblivious transfer, and once you have oblivious transfer, you can use it using Garblin's scheme to evaluate every function that you want. And the one thing is the equality that you need for that has at least, I mean, x1 and x2 have to come from a domain of size at least 3 in order to do that transformation. So let's show how to do that. We want to compute equality, and we start by just staring at this formula at the top of the slide, which you should think about it as x1 and x2 are the inputs, s1 and s2 are randomness. And you should think about it as S1 plus S2 times S1 minus S2 with the input thrown in somehow. You open parentheses, you arrange it somewhere, and you see that there are green terms that look like sums of terms that the parties could have generated by themselves, and then a cross term. And the cross term goes away when x1 is equal to x2. So that suggests a very simple protocol. The two parties will just take the three values that they can compute on their own, put them in a vector. So party 1 will output S1, x1 times S1, and x1 times S1 square, and party 2 will do the same with some minus signs there. The evaluators see the sum of these two vectors. And all it needs is to check whether the first sum times the second one equals the second. So that's a very natural protocol. No cryptography involved, but it's sort of broken. I mean, it is broken, not so. The problem is if you stare at it long enough, you'll see that not only you learn whether x1 is equal to x2, you actually learn from these three sums the difference between them. How do you fix it? Well, you put everything in the exponents. Once you do that, the evaluator still needs to compute the product, so you need bilinear math for that. So this gives you that protocol. We have these G1, G2, and GT, which are the generators in the two source groups and the target group of the bilinear map. The protocol otherwise is exactly the same, except instead of S1, you give the image of S1 in the first group instead of S2, etc. And the evaluator gets the three sums, and it needs to check that the product of the first two equals the third, which it does using the pairing. And then you can prove that assuming some assumption which is weaker than squaring version of XDH, this protocol is an additively random encoding. The thing really to prove is that when x1 is not equal to x2, what you see is a pseudo-random vector. When x1 is equal to x2, you get the exact right distribution, but otherwise you get something which is only pseudo-random other than random. And under this assumption, the evaluator cannot tell it. So now we have a protocol for equality. And the next thing we want to do is show a protocol for oblivious transfer, but actually we do better than that. We show that equality is ARE complete for binary function with small domains. Every function whose output is 0 and 1 and the truth table is small enough, you can compute using equality. Technically, it's the easiest lemma in the paper, but it somehow as a statement, it's a very surprising statement. So this is how you do it. Think of P2. P2 has its own input x2, and it knows the truth table of the function. So it takes all the x1 primes that would have yielded an output of 1 and lists them, and then just run equality for each one of them against the real input of the first party. And then you output 1 if any of them is 1 and 0 otherwise. That's basically it. For security, you need to do a little more. So you need to pad this list so that the length of it doesn't depend on the output. And you need to shift it by a random amount so that the position where the 1 is doesn't leak anything. But other than that, this is all there is. So we have every small function you can do using equality, in particular the oblivious 1 out of 2 oblivious transfer function. That's a function with 1 bit of output and a small truth table, so you can do that. Just as an aside, you can go directly to oblivious transfer. Really. You didn't have to go through this completeness theorem. Just the protocol that I already described If you just tweak it very little, what you get is the Rabin oblivious transfer function out of it, and then you can get one or two oblivious transfer easily. So good. So we have additively randomized encoding for oblivious transfer, and now all we need to do is use garbled circuits to get everything else. The way we do that, we allocate to each party a position within a vector. The first party would be the one in charge of generating the garbled circuit. It will put the garbled circuit with its input hardwired in the first coordinate, and will run this two-party oblivious transfer versus each one of the other parties. The evaluator gets the garbled circuit in the first component, gets the thing that lets it compute the oblivious transfer output in all the other components. Now it knows one label from each wire, and it can evaluate the garbled circuit and get the output. So putting all of this together, we have the theorem that says that every n input function has a computational additively randomized encoding scheme under the same assumption that we needed before, which is something slightly weaker than squaring XDH. Good. So this is the theorem that I wanted to show you, and let's talk a little bit about implication of that. And in particular, let's think of the shuffle model. The shuffle model was introduced by ICOS almost 20 years ago. And it was a model for leverage anonymity in order to get secure computation. The way to think about it is parties have access to an anonymous bulletin board on which they can post messages. So they post messages to their hat content, and later on the evaluator comes, looks at the bulletin board, sees all the messages. It doesn't know who sent what message or what order they were received. All it sees is a set of messages unordered, and from that it should be able to deduce the value of the function and nothing else. So really what it is another variant of randomized encoding, right? Every party takes their input, encode it as a sequence of messages, then you put all of these messages in a hat, you shuffle it, you throw out the messages out of the hat, the evaluator takes the unordered or randomly shuffled set of messages and needs to compute the function, and you have the same correctness and secrecy requirement. The value of the function is the right one, at least with high probability, and given the output of the function, a simulator can compute the same distribution or computationally indistinguishable distribution of these messages. And ICOS and then others show that, in particular, computing the sum is possible in the shuffle model. So putting that together with our theorem from before, you get that you can compute every function now in the shuffle model. And the way it works is you first do the encoding phase of the additively randomized encoding. Now all you need to do is to compute the sum of it. That you do in the shuffle model. Then now that you have the sum, you do the decoding of the ARE to get the value of the function. And if you look inside of the shuffle model, there is another level of encoding and another level of decoding and the shuffling. So let's talk about differentially private schemes. One concept in differential private research is it's nice to have a differential private scheme, but it's very centralized. Everybody needs to give their true inputs to this mechanism, and then this mechanism draws randomness and computes this differential private output out of it. But it is a central mechanism, you trust it a lot. Would be nice if you can trust it less. And the shuffle model came up as one thing where we can do things where you need to trust some centralized mechanism only in order to shuffle the messages, which, maybe the network takes care of it, maybe something else takes care of it. So maybe you get less trust in the centralized authority this way, and you can still obtain differential private mechanism. So from our point of view, well, if you can compute every function that you want, then you can compute every differential private mechanism that you want. It's just a function. Well, not exactly. You need to choose randomness. So somebody needs to do that. Again, let the first party do that. So here is the compiler from any centralized differential private scheme to shuffle model differential private scheme. You let the first party choose randomness. Then you apply the theorem that says that every function can be computed in the shuffle model to the result. And if you open everything else, then you see that what happens is there is a phase of encoding, which for the first party includes choosing the randomness, then everybody do their ARE encoding, then everybody do their shuffle encoding, then you shuffle, and then there are these levels of decoding. So they first do the decoding of the shuffle model to get the sum, and then you get the ARE decoding to get the value of the function. All in all, you have local processing followed by shuffling, followed by decoding, followed by getting the output of the function, and the output of the function is the differential private mechanism. So you get differential privacy in the shuffle model for every function. Now that's the non-robust version of it, where you only want the output to be indistinguishable from and only want the output to not be more information. Right. That's more or less all I wanted to talk about for today. In the paper, you can also see other things like a statistical additively randomized encoding for the cap sum function, which is you want to compute the sum of the function, but only if it's below some threshold. If it's above the threshold, the only thing you want to learn is that it's above the threshold, not how much it is. We have some characterization of perfect AREs in terms of what we call vector multiplication programs, which are essentially just the DFT of the corresponding probability distribution. And we use that to prove lower bounds on additively randomized encoding scheme, perfect additively randomized encoding scheme. In particular, we show that capped sum does not have a perfect additively randomized encoding scheme. So we have a separating example where you can do statistical but not perfect. We also try to extend some of the impossibility result to the statistical model, but basically failed. I mean, we proved something, just not what we wanted. You can find it in the appendix if you want. Even more things. We have this notion of robust ARE, where you want security even against a collusion of your evaluator with the input parties. As I said, it implies obfuscation. We can build it in the ideal obfuscation model. We show that statistical robust ARE for a function implies this notion of best information theoretic entity for the same function. This is a notion from a couple of years ago. We have a connection of robust ARE for all simple functions. Simple is whatever the slide says. It implies a degree 2 of multi-party randomized encoding, which is optimal. All of this you can find in the paper. Right. So what we did here, we described this notion with these variants of perfect statistical computational, robust or not, positive and negative result. In particular, on the positive side, every function has a non-robust computational ARE and applications and connections to other notions. And I want to conclude with a few open problems. Perhaps the most interesting one is what happens with statistical ARE. For all we know, it's possible that every function has a statistical ARE scheme. We strongly suspect that that's not the case, but we were not able to. If we go to computational ARE, we have one construction from one type of assumption. Can we get it from other assumptions, at least LWE? But if we are already going there, why not from one-way functions? And the notion of robust ARE, we describe a construction in this ideal obfuscation model. We know that it implies I/O. Can we construct it from I/O? We don't know. Can you even from DT for black box obfuscation? I don't know how to construct it. So that's all I wanted to say. Thank you.
Okay. We have a few minutes, so are there any questions? Over here, can you come up to the mic perhaps? Or... Okay. Or we can pass the mic up maybe, yeah.
So you mentioned that you get AREs for all functions. Shouldn't this read for all permutation invariance functions? Because if you consider like xi lesser equal xj, this would obviously not be possible in the shuffle model because shuffling would swap the house of the function.
So it's a good question, but the encoding, not all parties have to use the same encoding function. When you encode things, you're allowed to know that I'm the third party. So the thing that you permute or the thing that you sum is actually not invariant under permutation. So it really is all parties.
Thanks.
Your question right behind you. Any other questions? So I guess I have a quick question if there's no line. So just in the differential privacy and shuffle model, like the protocol you described where party one adds in the noise. Is it differentially private with respect to party one or?
No, it's not. This is the non-robust version
I
of
see.
differential private mechanism in the we don't have a robust, like even robust ARE doesn't imply robust differential private mechanism. So that I should have had that as a matching problem.
Okay. So anybody else have any questions? Okay, well, in that case, I'll thank the speaker again. Thank you.